Hi, everybody, and welcome to RISE Learning Machines seminars. I am Olof Mogren, and I'm a machine learning researcher at RISE. RISE is Sweden's public research institute, and this is our open weekly seminar on AI and machine learning. This meeting will be recorded. Let us know if you want to be removed from this recording. Also, check out the collection of great talks on our YouTube channel. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers in the Nordics working in the intersection of climate research and AI. Today, I have the pleasure to introduce to you Atakan Aral, who is assistant professor at the University of Vienna. Atakan received his master's degree in computer science and engineering from Politecnico di Milano and Istanbul Technical University. And he obtained his PhD in computer engineering from Istanbul Technical University in 2016. He has also been a postdoctoral fellow at the data science group at TU Vienna and an assistant professor at Umeå University. Working on optimizing resource utilization and placement at the network's edge for data-driven workloads. The topic today is Edge AI and IoT-driven water quality monitoring. And with this said, I will stop my screen sharing and hand over the stage to you, Atakan.
Thank you very much, Olof. Let me share my screen. Okay, it should work now. Oh, no, I'm sharing the wrong screen, I guess.
Yes, we see the presentation mode.
Let me try again. Yeah. Okay.
Yes.
Thank you very much again. Yeah, thank you for the introduction. As Olof said, I'm with the University of Vienna at the moment as an assistant professor, but some of the research that I will talk about today was conducted at Umeå University, my previous affiliations of Umeå University and TU Vienna. Today I will talk about Edge AI and IoT-driven water quality monitoring. And let's start from bottom up and from top. That start with environmental monitoring, the definition of it. So according to the UN definition, environmental monitoring is a tool to assess environmental conditions and trends, to support policy development and its implementation, to develop information for reporting to policymakers, public, etc., and to achieve real-time decision making. This aspect especially is relevant to my work, real-time decision making, and it is enabled by recent rapid advancements in Internet of Things and machine learning technologies. More specifically, I will talk about remote environmental monitoring. And by remote, I mean two different aspects of remote monitoring. Not to be confused with remote sensing. It is an entirely different concept. So the first definition of remote environmental monitoring is that we are collecting data in geographically remote regions where we have limited infrastructure of electricity, energy, and network. For example, when we are monitoring water pollution, which is the main topic of this talk, or forest fire avalanches, we have to collect data from very remote areas with challenging conditions. The other aspect of remoteness is that we are using IoT systems to gain real-time insights remotely. So the processing is not happening where the data is collected. We have sensing equipment, sensors, IoT devices, etc., communication equipment to transmit the data, sensors to gateways, and we also have the processing equipment. It could range from as small as Raspberry Pis to massive data centers for remote processing. So some example, I will start with a brief mention of a few examples of remote environmental monitoring. This is a categorization we made in our recent paper where we analyzed the literature on or recent projects from governmental organizations and research projects on rural or remote environmental monitoring. One of the examples, I will go through these examples very quickly, not to take too much your time. I guess the slides could be shared so you can follow the links on your time. So this project is about air quality monitoring worldwide by United Nations Environmental Program, where you can track air pollution in real time on a web interface. This project is also for air quality monitoring by University of Helsinki, at the city of Helsinki, where they use 5G technologies to sense air pollution in mega cities. When we come to water quality management, one example is my own project, SWAIN, Sustainable Watershed Management through IoT-driven artificial intelligence. I will talk in detail about this project, so there's no need to tell you more at this point. I will come back to this slide as well. Another water quality monitoring project is Waterline, which uses remote sense data to predict flows and water levels on Greece mainly. There are, of course, many seismographical institutes tracking the Earth's movement for earthquakes. One of them is European Mediterranean Seismographical Center, for example. Or there are avalanche monitoring, snow monitoring research. This example is from Switzerland. IMIS, Intercantonal Measurement and Information System. And maybe one of the largest deployments of remote environmental monitoring is by Comprehensive Nuclear Test Ban Treaty Office, CTBTO. It is not the largest in terms of number of sensors or number of facilities, but how large an area it covers, because it covers the whole Earth. Basically, they have sensors from Arctic to rainforests all around the world. And here you can see their deployment almost homogeneously, all Earth is covered. And the data collected from this is to detect nuclear tests, which are banned by in countries that signed this treaty. And they also use this data for tracking climate change. The same sensors also help with tracking climate change as well. So this was a fast run through on different aspects. If you are interested, I recently published a paper on Environmental Data Science Journal where I analyzed these different remote environmental monitoring use cases in terms of what is their real-time constraint, how rural they are, what are the potentials for access to the network or power grids, etc. So, and a specific aspect of remote environmental monitoring I want to talk about is the sustainability. So for environmental sustainability, monitoring is crucial because we can use it to track environmental changes, inform or automate actions, or provide better understanding of environmental phenomena. But the monitors themselves should be sustainable. And the question is, how can we make sure that the monitoring systems are sustainable and are not interfering with the environment? So this is the image created by generative AI when I input IoT-driven environmental monitoring. And this is, of course, the opposite of sustainable way of doing this with thousands of sensor communication networks all around the natural environment. Of course, this is not our goal. And we aim to make this system have as small footprint as possible. And as promised, I now come back to this SWAIN project, which was concluded last year at the University of Vienna. It was a 3-year project, not only in University of Vienna. It was a international project with Finnish, Swedish, Turkish, and Austrian partners. And it was also interdisciplinary with environmental scientists involved. So the idea in this project was to deploy measurement stations in downstream rivers in multiple locations and collect water quality data, not only to detect pollution, but also to backtrack measured pollutants to their potential sources. So to do this, we had a data-driven model of the river, the flow of water in the river, and based on the data we calculated, we predicted the approximate location of the pollutants. And what we did was to collect this data at the measurement station and process them at nearby server called edge servers, if you are aware of edge computing. And these edge servers can be co-located with the measurement stations, or they can cover multiple stations in a small geographical area. And the data was pre-processed on this edge server. Then intermediate results were sent to a remote data center, a cloud data center, for example, for more computational capacity. And then once we detect a pollutant and we know the potential source of the pollutant, we warn the authorities, and we let know the authorities, and they send a warning system to the potential facilities that causing this pollution. And this was motivated by several environmental disasters in Europe where the pollutants were detected many days later after the environmental impact was already in place. For example, they detected the pollution after fish died or mussels died, and then they took precaution. And the idea was to have this kind of early warning system to prevent environmental disasters.
Question?
Sure, please.
What kind of pollutants are you considering here?
The idea in the beginning of the project was to focus on micropollutants that are in low concentration but still have significant effects on human health, and if the water is used for agriculture, also for crops. But throughout the project, the idea has changed a little bit because I think we were too optimistic and we assumed that we knew that we cannot monitor micropollutants. They are not real-time sensors for them. But our idea was to use some fingerprint chemicals that we can monitor, and we could match them to the micropollutants, and then we could figure out or infer micropollutant as well. Unfortunately, this didn't work very well, and then we changed the scope to more traditional or more conventional chemicals or pollutants like heavy metals or this kind of pollutants mainly.
Okay, thank you.
Okay. Yeah, I forgot to say at the beginning that please feel free to interrupt if you have questions. You don't need to wait until the end. So when we think about sustainability of such a system, we usually think about energy efficiency, because it's a popular topic at the moment that the data centers or large language models consume a lot of energy. And of course, it is natural that we consider that as the first step. But I will focus on also other aspects of sustainability beyond energy efficiency. For example, availability or non-availability of energy or network infrastructure could be a sustainability issue, especially when you need to bring network or energy through cables to this area. Or if you opt for battery options, then the disposal of these batteries and maintenance is a problem. The same idea goes for the hardware. It can become obsolete over time and produces e-waste, which needs to be collected. And as I said before, we are talking about remote areas that could be hard to reach to go and collect or replace these devices. So all of these might cause to physical disruption to ecosystems. And some of the solutions we came up with in this project were energy harvesting to avoid batteries and to also to avoid energy infrastructure brought to the rural areas. We were lucky that we were working on water systems then, because it's a river, so it's running water. It is easier to harvest energy compared to solar energy, where you have to you would need a battery to be able to continue working at night, for example. We also made several optimizations to reduce the number of sensors, to reduce environmental footprint, to reduce the amount, the communication, to avoid more dense deployment of network architecture. And we also worked on more efficient processing, so energy efficient processing of data. So I will talk about these aspects in the next 3 parts of my talk. So I will start with minimizing the footprint of sensors and gateways. What we did was to have a spatial planning of sensors and gateways to optimize the quality of data that can be collected, the reliability of data, maintainability of it, but at the same time having as few sensors as possible. And our 2 case studies were from our partners in Turkey and Finland. The one on the left is the Ergene River. I don't know if it is too small to see, but here you might see some red dots. These are industrial developments in the upstream river. And in the downstream, these orange areas are agricultural fields, where the same water is used for agriculture after the industrial deployment. So if any risk of pollutants here will directly reach the crops. And similarly, in Kokemäki River in Finland, there is a large nickel industry that use river water. And at the same time, the region of Turku consumes artificial groundwater originating from this river, Kokemäki River. So timing is critical again here to detect pollutants, because it is estimated that pollution from upstream can travel to the water intake point of city of Turku from 20 minutes to up to one hour, depending on water flow speed at that time of the year. So our solution was a multi-objective one, because as I showed here, there are different objects to optimize. Again, this was a collaborative effort with our project partners, and therefore we had separate modules developed by different partners, and then they were combined by as shown in this schema. We call it GANS framework with the because of the first letters of each module: gateway placement module, energy modeling module, sensor placement module, and network modeling module. And our work was mainly focused on sensor placement. So having less sensors, but collecting a similar quality data was our focus. And what we did was to use column pivoted QR decomposition approach, which is an algorithm that looks at large matrix of environmental data. For example, the columns could be possible sensor sites, and the rows are the historical pollutant measurements on these sources. And we factorize this matrix to find which columns carry the most unique information. It is, it can be similar to dimensionality reduction or feature selection approaches that we see in conventional federated learning. But the idea here was to pivoting these columns during QR decomposition so that we can select a set of sensors that can best reconstruct the whole environmental signal. And with this, we started with 70 sensor locations around one of our case study rivers. We deployed the network infrastructure first with gateways, and then selected the optimum sensor locations in terms of data quality, but also closeness to these gateways, and managed to achieve comparable accuracy to 75 sensors with only 30 sensors. Here you can see our approach shown with red line reaches the optimal location of unique micropollutants detected accurately. It is almost reached the maximum point with only 30 sensors deployed. And this results in 60 to 73 fewer IoT nodes deployed in the environment, and almost the same number of accurately detected pollutants with 60% energy savings. So if there are any other questions, I will now move to another optimization we have done, which is minimizing the communication overhead. So as I said, when we reduce the number of gateways and network links, that gives us a very limited bandwidth, especially if we are using energy efficient communication protocols such as LoRaWAN. The bandwidth is very limited. And therefore, the idea of local processing was quite helpful in reducing communication overhead. So our idea was to process the collected data at an edge server locally and only transfer the model updates into the remote data center, because the bandwidth between the measurement stations and edge servers are not the problem. The transfer of raw data to the cloud is the problem, because in local area we have more flexibility, have better bandwidth in comparison to accessibility to the core network. So the idea was, instead of transmitting raw data, we pre-process data and only send updates to remote data center. And this is called edge intelligence or edge AI. You might have also heard federated learning, which is a subcategory of edge intelligence too. And the idea of edge intelligence is that it is edge computing with machine learning and advanced networking capabilities according to the definition of international electrotechnical communication. Or a more informal definition is that instead of entirely relying on the cloud, edge AI makes the most of widespread edge resources to gain AI insights. It usually consists of a 3-layer architecture with devices that generate data. In our case, these were sensors, water quality sensors, which has the highest amount of data, but smallest computational capability to run complex AI models. And then in the middle, we have edge server with less data, but more computational capability. And then cloud server ideally has fewest or even no raw data, but the most complex model to be trained. And edge servers are preferred because they are closer to the data sources. Sometimes they can be co-located. In our case, the measurement stations had their edge servers already inside of them, Raspberry Pis. And this allows higher data transmission rate, and but at the cost of lower computational power. And this is a categorization or classification of different edge AI approaches. So this is the conventional way of running real-time AI models, is to send the data to a remote data center and do inference and training on the cloud. Then you can have inference on the cloud and training, inference at the edge and training on the cloud, and all the way up to doing everything on the device or everything at the edge. Our approach was more level 4, which is cloud edge co-training. So the training was done at the edge partially, but rest of it was done at the cloud. And inference was completely on the edge nodes. Here you see our system diagram where we have various data sources that send streaming data to nearby edge nodes, which train local models based on their local data. So this can be, for example, representing a part of the river that the data is coming from. And then this happens, of course, continuously, this data transfer. Then these models are periodically sent to the remote data center, sometimes called parameter server in federated learning literature. In parameter server, these models are combined to a more global, more generalized model. And then again, periodically, they are replicated back to the edge nodes, and they continue training from that point. This allows each model at each edge node has also the information from the other nodes, but it is also specialized to that data source coming from it. And in this architecture, we focused on a problem that we called staleness problem. So staleness is about how quickly a data is incorporated in the global model and how much time can we delay to optimize network communication. I will explain this with an example here. So let's consider a very small scale example with 4 edge nodes. And upper side, you see a timeline which will show the update arrival times to the parameter server. So when parameter server has a new update. And at the bottom, we will see the charts of accuracy over time. So let's assume that initially there is a model at edge nodes, and initially at time t0 we have updates from 2 models, and two updates are missing. This is very probable because we are in a very rural area. The network communication is not reliable. Sometimes devices are offline because of energy unavailability and so on, so that many updates could be missed. So at the parameter server, we can decide to build the global model already with missing data and then update the edge nodes immediately. And if we wait, the accuracy of the edge nodes will drop over time because of staleness. The model is not fresh anymore, and the environment is very dynamic. So if we update, we will probably have a better accuracy at that point because it is augmented with newer data, and then it will continue to drop. Another option could be wait a little bit longer, and maybe we will have another update from another edge node. At this time, we still have this old stale model during this period, and at time T1, we have the new model. The new model could be better compared to the first option because it includes more data, it is more generalized from different sources, but you have to tolerate the stale model for a longer period of time to update at time T1. And as you can imagine, the last option is to wait all the way until all updates have arrived and then update the global model only at that time. So conventional federated learning approaches work like this. They wait for all updates to arrive. And only when all updates arrive, the global model is distributed. But very recently, there is also an approach called asynchronous federated learning, which applies a similar approach that we did here. But yeah, this work was 5 years ago. So we didn't even call federated learning at that time. We called it, I think, distributed data analytics or something like this. So to solve this optimization problem, and very intuitive solution for it is to integrate these graphs and calculate the area under these joint charts to find the optimum solution to choose to go for which option. And yeah, this is basically our optimization function from T0 to Tj. We use the utility function. It could be accuracy, whatever utility you have, and plus the utility from that time until the end of the iteration. And our hypothesis was that there exists a point to broadcast the new model within each iteration that yields optimum accuracy. And also our hypothesis was that this point is not fixed. So we cannot use, for example, a quorum approach saying that if 50% have arrived, we can just broadcast the model. But our idea was that this point can be different depending on which order these updates have arrived and what is the quality of or information quality of each update. So to solve this problem, and it's a very dynamic problem because we don't know which update will come next. We don't know how informative this model will be. We even don't know if an update will ever come. We might decide to wait, but no updates might have arrived. So we modeled this problem as a Markov decision process with states represented with. So I'm continuing the same example from previous slides with 4 nodes. Here 0011 means 2 updates have arrived and 2 updates are missing. And then we have the transition function, which uses Hamming distance of 1 between the nodes. So if we decide to wait at this point, we might have this update or this update. It is unclear which one will arrive. Or if you decide to wait longer, we will have all the nodes. Or at each point, we might decide to choose the action push, which means basically I decided to build the global model at this point, and I don't want to wait any longer. And then we end the decision process here. In addition, there are self loops in these nodes, which means that even if you wait, you might not transition to the next stage. It is possible that one of the edge nodes is permanently inaccessible, so you will never get a new update. The next thing in Markov decision process is the state transition function, which is this, which is what I described here in this chart. And finally, we have the reward function. And in our case, the reward function was only awarded when we choose the push option. And when we choose this option, the reward would be the accuracy or utility of this model. And it was directly proportional to the variety of accumulated data from how many sources it arrived, and inversely proportional to time elapsed, because we also don't want to lose freshness for too long. And there is also a penalty when we decide to wait, but the state hasn't changed because we wasted time, basically. We could have broadcasted the model earlier, but we waited for new updates which have never arrived. And then we run an online Q-learning model, online delayed Q-learning model on this decision process. Delayed Q-learning means the updates to the Q metrics are delayed until a statistically significant number of experience is reached. And when we use this delayed Q-learning, we can put a theoretical bound on convergence of Q-learning. So I will not go too much into detail of Q-learning. This is standard in the literature. And these are some of our results. Again, I will not spend too much time on these. Maybe just a summary of our results. We showed that we can achieve comparable accuracy to core AI, which means collecting all the data in a single data center and processing it all together there instead of distributed processing. Our accuracy was comparable, yet the responsiveness was real time. So we measured responsiveness with a metric called age of information, which shows how fresh is the information, and we managed to keep it until 10 seconds in our experiments. And another aspect is that we had low communication overhead. We only had one update per minute. This is very useful in, as I said, low energy consuming communication protocols, especially downlink communication is problematic, where the global model is distributed to the edge nodes, and we managed to make it as infrequent as possible. Then the final part of my presentation is about minimizing energy consumption. And first of all, before explaining how we made the model more energy efficient, I need to tell you what kind of models, what kind of machine learnings we deployed. For this problem, we deployed graph attention networks. You might have not heard about them, but you might have heard more popular version of, or more general version of, graph convolutional networks. They are very similar attention networks. The only difference is that in graph convolutional networks, all neighbors are treated equally, and we use the weighted average of their features, averaging their features, for example, using the weight of the node in the graph. Whereas in graph attention network, we have an attention function to assign difference importance to each neighbors. And in our case, this graph representation was natural because the river network forms a graph structure, and the water flow can be represented as nodes and links between these nodes as well. So the problem of energy efficiency is that this graph attention network could be very large, and we are not able to run or train this model at each location where an edge server is located, because, as I said, our edge servers could be as small as Raspberry Pis. And one of the ideas we used here was DNN partitioning, where we split the DNN. This is not our contribution, by the way. This is an existing methodology that has been around for a long time. But again, recently, this has become more popular with federated learning. And this is called federated split learning now. But previously, this was called DNN partitioning. And here you run a few layers for initial layers at the edge nodes or devices, and then you transmit the intermediate data to the remote data center with more computational capability and run the remaining layers there. And yeah, for example, in our approach, depending on the computational capability of each measurement station, we can run, for example, here, we run 5 layers and then the rest at the cloud. Or here, maybe it is less computationally capable. We run only 3 layers and then run the rest at the cloud data center. And then we save a lot of energy at the edge nodes. And in clouds, usually cloud data centers are using more green energy, hopefully, so that saving energy at the network edge is important here. Also to avoid, as I explained before, also to avoid batteries or building infrastructure for electricity. Another approach that we used in our project was early exit DNN. And this means the neural network has multiple exit points that are called side branches. And these allow inference to stop at an early intermediate points if we are confident enough with the results. So we don't need to run the whole neural network, but we can stop earlier if the accuracy or confidence is high enough. And we use the combination of these two approaches, so split learning or DNN partitioning and early exit together. So for example, we run 5 layers. If we are confident enough, we can already finish here and no transmission to the cloud. Or if not, if we are not confident enough, we continue the processing at the cloud and so on. Yeah, that is more or less what I want to tell you about today. Maybe a few take-home messages on my presentation. So thanks to these recent developments in IoT and edge AI technologies, now large-scale environmental monitoring is feasible. And sustainability can go beyond energy efficiency. A lot of optimizations are possible for long-term monitoring solutions, both preserving AI performance and achieving sustainability. But we also noticed that collaboration is crucial in this area because it is an interdisciplinary topic. So cooperation between AI researchers, computer scientists, engineers, policymakers, and environmental scientists is very useful. And from this, we benefited significantly in our project. So thank you very much for listening to my presentation, and I am looking forward to your questions.
Thank you, Atakan. Do we have some questions from the audience?
Yes, please. Can I have a question?
Yes.
Thanks for your presentation. I have a question related to the gateway parts and the sensor parts. It seems that part is something like the random access network. There is a multiple sensor around the gateway and transmitting data to the gateway. As you told, and as we know, the main important things for federated learning is updating the model as soon as possible.
Right.
I didn't see any policy for selecting the node, selecting the user, when to send the data to the gateway. Is there any policy for selecting which sensor should send its data to the gateway to starting the training at the edge? And because there is interference between the nodes, maybe you are using the Wi-Fi, which is working at 2.4 gigahertz. The interference between the data maybe affect on the training. Could you please, what kind of the policy you use for this project? Thank you for your presentation again.
Thank you. Thank you for a very interesting question. In our case study, the sensors were not smart, so they didn't have their computational capability. That's why they were sending their updates continuously to the gateway. So they didn't have a selection mechanism which information to forward, but the sensor is in a nearby location, so the bandwidth was not a significant problem there. The only decision making was about the communication from the gateway to the cloud data center, and this was optimized at the edge nodes. Therefore, there is no policy regarding which sensors or which nodes send the updates to the edge node.
Thank you very much.
In the previous example, when you were deciding on whether or not to push the updates, in that setting, what do you do in the training if you push an update that's not complete? What happens in the training? You only train with the clients that have updates.
Yes, and the assumption is that maybe in the next iteration, the other missing nodes will be available, and then this will balance it out. So we only use we only average the available models as a global model.
Okay. Thank you.
Okay. Because the other way of doing it is always waiting for all updates to arrive. Because in more conventional setups, like where everything works perfectly, they usually arrive at the same time, or more or less at the same time, and this is usually not a problem. But in our case, because we are in a very unreliable environment in terms of network and power, this problem could happen very frequently.
Can I ask you another question related to age of information? You mentioned about age of information. It seems this system just broadcasts the models, not the raw data, with the server. In which part of this project the measurements are transmitted to the server? Based on your presentation here, we just see that the model is broadcasted and transmitted to the server. And where the age of information is considered here?
Yeah, we consider age of information from the time the data was collected at the sensor, all the way it is sent to the gateway, included in the local model, sent to the parameter server, included in the global model, and then broadcasted back to the edge node. So endpoint is when it is broadcasted and arrived at the edge node. And at this point, we assume that this information is incorporated to the model. And we measure the time from its generation to that point. This was our definition of age of information. But of course, different definitions are possible. Does this answer your question?
Yes, yes, I know the definition of the age of information. The main question is, do you transmit the raw data? Because
no, only the model updates.
So the age of information is related to, it means age of model, it means not age of information of the raw data, you mean, in this system.
Or age of raw data that is incorporated into the model. But data itself is not transmitted. Yes, you are right. Technically, the data is not transmitted, so we cannot talk about age of information for the data. But yeah, this was our definition of age of information.
Okay, thank you.
The data itself, raw data itself, is not transmitted, but the model that includes that data is transmitted. So it's not direct, but indirectly, the data is also going to the parameter server.
Thank you.
All right. Do we have some more questions? I have a technical question on the early exit networks. That's you use them to save compute, I suppose. So if you're happy with the output from the exit one, then you will not do the rest of the compute.
Exactly.
Okay. And how do you what's the criterion for being happy with the exit?
Yeah, there are different approaches. Maybe the most common one is to use maximum softmax probability. If the maximum softmax probability is high enough for above a threshold, then we decide that it is confident enough. Of course, this probability can be overconfident sometimes, but this is the simplest approach. There is also approaches that use entropy to measure how uncertain the classifier is. If entropy is low, the model is confident and exits early. If it is high, it continues to deeper layers.
Okay, thank you. Okay, so I think that we should conclude for today. We have a seminar again next week. Welcome back then, next Thursday at 3. And thank you again today, Atakan, especially for your presentation, and everybody who attended.
Bye-bye.
Bye.